Hi class, it's me, Mr. Morris, and we're doing a video today on doing Lewis dot structures for covalent compounds. By now you've learned how to name covalent compounds, you've kind of learned what they are, but we're going to learn today how to draw structures of them. This is an important skill for the rest of the class, or for the rest of this unit at least, because everything else after this in the unit pretty much depends on your knowledge of how Lewis structures work. Covalent bonds, again, are a bond between nonmetal and nonmetal where they're sharing valence electrons. And there are three types of substances that contain covalent bonds. This is something that's maybe new to you. The first one is kind of obvious, covalent compounds, but also polyatomic ions can contain covalent bonds, and so do diatomic elements such as H2, O2, and N2. The octet rule, this is review again, it's all atoms want to achieve 8 valence electrons, but there are 3 notable exceptions I want you to know about. Hydrogen wants to achieve 2 valence electrons. By the way, hydrogen is the most common exception. You're going to see that one a lot. So if you just memorize one of these, hydrogen's the most important, but you do want to memorize all of these. Hydrogen wants 2, beryllium wants 4, and boron wants 6. Now, I get the question from students most years, what's the deal with beryllium? I thought it was a metal, not a non-metal, so why are we talking about it in the covalent bonding unit? Well, beryllium is a metal, but it's one of the metals that is kind of unique, that occasionally will bond differently than the way we expect. So it sometimes bonds as if it is a non-metal. So I say sometimes beryllium loses its mind and thinks it's a non-metal. Anyways, I'm not going to trick you with beryllium compounds. If we give you a compound with beryllium in this unit, you just need to assume that it's a covalent compound. I do want you to know these 3 exceptions though. Hydrogen wants 2 valence electrons for each hydrogen atom. Beryllium wants 4. Boron wants 6. The symbols for bonds and for pairs of electrons are as follows. A bond is represented by just a line that's a bonded pair of electrons, and it's 2 electrons, and a lone pair of unshared electrons. It's also 2 electrons, but we show that with 2 dots. So each dot is 1 electron, 2 dots be 2 electrons, and a line shows 2 electrons that are being bonded or shared between 2 atoms. Now the skeletal structure, we're going to talk about that a fair amount throughout this lesson. It's just an arrangement of the elements that tells who's in the middle, and it's connected by bonds. Okay. Hydrogen is never in the middle. The element that's first mentioned is usually in the middle, and if there's more than one, they're also in the middle. This last part where it says if there's more than one, they're also in the middle, we're talking about compounds similar to this one right here, N2H4. There's nothing that there's only one, neither of the elements are there only one of them. Okay, so we've got 2 nitrogens and 4 hydrogens. The first one mentioned is the central atom, and we have both of those in the center. So we have N2, so 1 nitrogen in here and 1 nitrogen there. That's the center, and the other hydrogens surround the nitrogens. Now let's do a little practice counting valence electrons with these examples that we have down here. Remember, each dot represents 1 electron, and each line represents 2. So if I wanted to count electrons in O2, I would go 2 for the first line, 4, because there are 2 lines, and 5, 6, 7, 8, 9, 10, 11, 12. It looks like we've got 12 valence electrons in O2. Look at H2O. We've got 2, 4, 5, 6, 7, 8, 8 valence electrons. All right, 2, 4, 6, 8, 9, 10. 10 valence electrons in HCN. And then with N2H4, I've got 2, 4, 6, 8, 10, 11, 12, 13, 14 total valence electrons. You probably noticed up here some double bonds and triple bonds. Let's talk about those. A single bond, that's just one line, like what we have here in H2O. Those are single bonds, or this one. Okay. It's got 2 valence electrons being shared. A double bond is 4 valence electrons being shared, which makes sense because it's twice as many lines, so it's twice as many electrons. So 2, 4. How many would a triple bond be, do you think? Well, if you said 6, you're right. Okay. Bond strength, we just want to know what's the strongest and what's the weakest. A single bond is actually the weakest bond. A triple bond is the strongest bond, and a double bond is somewhere in the middle. Okay, so it ranges from weakest as single bond to strongest as a triple bond. And you can think about rubber bands as an example of this. If you're trying to pull on rubber bands, you've just got one rubber band, that's going to be the weakest. But if you have 3 or 4, the more rubber bands you've got, if they're about the same length and you try to pull them apart, those the stronger the bond that's held by those rubber bands. Now let's think about the bond length. Well, the bond length is going to be kind of the opposite of that, because if it's a weak bond, thinking back to the rubber bands, a weak bond, you can stretch a rubber band pretty far, but if you've got a lot of rubber bands, it's harder to stretch them very far, so they tend to be closer together. It's a shorter distance. So our longest bond is a single bond, our shortest bond is a triple bond, which is also the strongest, and of course the double bond is somewhere in the middle. Now let's talk about rules for drawing Lewis structures. This is the main focus of today's lesson. There's some vocab that we need to get through, but this is the main focus. There are rules for how we draw Lewis dot structures, and we're going to follow a pattern. And I've got just kind of titles to hopefully help you remember it. The first rule is toolbox. That's just getting your tools together, figuring out what you have available to work with. Okay, this is where you count the total number of valence electrons available for you to work with. Pay attention to the overall charge, because negative ions gained electrons. That means they'll have extra electrons. If you have a positive ion, if it's a positive polyatomic ion, it has lost electrons, so you'll have fewer valence electrons than expected. Okay, the skeleton is our next step, our second step, and it's got 2 parts. The first part, we're going to put the singleton atom, the singleton element, it's usually the first element, in the center with all of the other atoms around it. The second part is we're going to connect those with lines. Use 1 pair of electrons to bond each outer atom to the central atom. And we're going to keep track of the number of electrons that we use in each step. And we can never use more than the amount we have in our toolbox. So when we find out how many valence electrons we have, that's the maximum number of electrons we can use in all of the remaining steps. So in the skeleton step, we're just connecting them with 1 line each. Outsiders. This step, we're going to complete the octets around all of the outer atoms. Those are the ones on the outside, not the central atom. Okay. There are exceptions. Remember, hydrogen only wants 2 valence electrons. That's 1 pair or 1 bond. Beryllium wants 4 valence electrons, and boron wants 6. Okay, so we're going to keep that in mind when we do step 3. But we want to make sure that all of the outsiders have the number of electrons that they want, whether that's 8, which it is for almost everything, or if it's 2, 4, or 6 for our exceptions. Leftovers. If we still have electrons left after step 3, we took care of the outsiders and we have extra electrons, we've not used them all, then we'll put the leftovers in the middle. We'll put them on the central atom. Keep in mind, we will sometimes put more than 8 valence electrons on the central atom. If it's in periods 3 to 7, we can have something called an expanded octet, where it has more than 8 valence electrons in the middle. Then step 5 says happy, question mark. Okay, so we're wondering, is everybody happy? So we check if all of the atoms have the number of electrons they want. If there are not enough electron pairs to give the central atom an octet, we're going to make double bonds or triple bonds. Now these can only be formed by carbon, nitrogen, oxygen, phosphorus, or sulfur. So an acronym to remember that is CNOPs, just in that order, CNOPs. Any of those elements can form double bonds or triple bonds. But we only do that if the central atom does not have enough electrons, and I'll show you how to do that in an example. Then we want to do a final count to make sure that all of the atoms have 8 valence electrons. Again, our exceptions are hydrogen, beryllium, and boron, because hydrogen wants 2, beryllium wants 4, and boron wants 6 valence electrons, not 8. Moving on to the next thing. Very last thing is putting the Lewis structure of a polyatomic ion in brackets. So if it's an ion, if it's got a charge, we have to draw brackets around it and then put the charge up at the top. Now let's look at pH 3. This is our first example. First thing we need to do is look at our toolbox. We want to count the number of valence electrons that we have and pay attention to the overall charge. pH 3 has no charge shown, so I don't need to worry about the overall charge really. It's a 0 charge. So we're just going to count the number of electrons. Phosphorus is in group 15, so that means it has 5 valence electrons. And hydrogen is in group 1, so it has 1 valence electron for each atom. pH 3 only has 1 phosphorus atom, and it has 3 hydrogen atoms. So we want to add those together. The way we do that is we're going to have 1, because there's only 1 phosphorus, times the number of electrons in phosphorus, which is 5, plus 3 times the number of electrons in hydrogen, which is 1. So we do it like this. 5 times 1 plus 1 times 3, or 5 plus 3, we end up with 8 valence electrons. 5 electrons came from phosphorus, 1 from each hydrogen, so 5 plus 3 gives us 8. Hopefully that makes sense. Then the skeleton. The skeleton, we're going to put the central atom in the middle. And the way we figured out our central atom, it's the singleton element and or usually the element that's listed first. Well, there's only 1 phosphorus, so that's one clue. The other clue is that it is the first element that's written. Phosphorus goes in the middle, and we have 3 hydrogens surrounding it. Okay? And that's what this says. I've drawn it out right there. Okay. The next step is we're going to draw single bonds from the outer atoms to the central atom. So we're just going to draw a single bond connecting each atom to phosphorus. All right, and we got to keep track of how many electrons we've used. Remember, in the last step, we decided that we were going to have, I believe it was 8. Let me check. Yes, 8 valence electrons. So we just used 6 of them, 2, 4, 6. I still have 2 to go. Our next step is outsiders. We want to put all the remaining electrons on the outer atoms until they've completed their octet. Remember our exceptions to the octet rule. Hydrogen wants 2 valence electrons. That's all it wants. Beryllium wants 4. Boron wants 6. Well, I have hydrogen as my only outer atom. Okay, it's the only outer atom in this structure, and it wants 2 valence electrons. Well, each of these lines is 2, so hydrogen doesn't want any more electrons. We get to kind of skip this step. All right, our leftovers. We're going to place any remaining leftover electron pairs on the central atom. So we could put extras on there if we have to. Okay. Now, we have 2, 4, 6 electrons used. We have 8 to work with, so we have 2 more electrons that we're going to put on the central atom. If there are not enough electron pairs to give the central atom an octet, this is the part where we say happy. Are they happy? If there are not enough electron pairs on the central atom to give an octet, we're going to make double bonds or triple bonds to make it happy. Now let's look. Phosphorus has 2, 4, 6, 8. It's already happy, so we're going to skip this step. The last thing we're going to do here is do a final count to make sure all the atoms have 8 electrons. We just did that for phosphorus, it's happy. And remember, hydrogen, beryllium, and boron, or if it's an expanded octet, those are exceptions. Hydrogen just wants 2 valence electrons. So let's check it. I've got 2, this one has 2, and this one has 2. So everybody is happy. For ions only, we would put brackets around it and then put a charge on the outside. Well, this is not an ion, so we're going to skip this step again. Our structure is actually complete as it is. Let's do one more example. CO3 with a 2- charge. You might recognize this as carbonate, the carbonate ion. Look at the toolbox. We want to count up the number of electrons that we have, the number of valence electrons, and don't forget about our overall charge. Negative ions have gained electrons and positive ions have lost electrons. This is a negative ion, so that means I have extra electrons. Because it's a -2 charge, that means I've got 2 extra electrons. So we need to keep that in mind as we add these up. Carbon has 4 valence electrons. Each oxygen has 6. CO3 with a -2 charge, it has 1 carbon atom and 3 oxygen atoms. And it also has a -2 charge, which means it's gained 2 extra electrons. So I'm going to calculate this by multiplying 1 times 4, because each carbon has 4 valence electrons, 3, because I've got 3 oxygen atoms, times 6, because each oxygen has 6 valence electrons. So 1 times 4 plus 3 times 6, and I have to have 2 extra electrons, so we're going to add 2 because of that negative charge that comes from extra electrons. 4 plus 6 times 3 is 18, plus 2. Add those up, you get 24 total electrons, and we need to keep track of how many we use as we go through. The skeleton. Which one goes in the middle? Well, carbon is the singleton, and it was written first. So we're going to do that, and we're going to draw single bonds to the outer atoms to the central atom, from the outer atoms to the central atom. So I've got CO3, carbon in the middle with 3 oxygens on the outside. We're going to connect it with bonds. 1, 2, 3 bonds. Then we want to do the outsiders. We're going to put all the remaining electrons on the outer atoms until their octets are complete. Remember, oxygen, like most atoms, wants 8 valence electrons. The only exceptions to that are hydrogen, beryllium, and boron. Oxygen's normal. It wants 8 valence electrons. So right now each oxygen has 2. We're going to continue to add electrons until we get each of those to 8. Outsiders first. So I had 2, 4, 6, there's 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, that was all of them. I only have 24 electrons to work with. So the leftovers step doesn't really apply because we used all 24. If we had leftovers, they'd go on the central atom, but there are no valence electrons remaining. We used all 24. We're going to skip this step. If there are not enough electron pairs to give the central atom an octet, we're going to make double and or triple bonds. Usually this can only happen between carbon, nitrogen, oxygen, phosphorus, and sulfur. Okay, so let's check. Does the central atom have an octet? Well, it has 2, 4, 6. No, it does not. It would like to have 2 more electrons there, but I ran out of electrons, so I can't just pull them out of nowhere. What I can do is make double or triple bonds, and when you do that, you're going to borrow an electron pair from somewhere. I'm going to get 2 electrons from over here and move them down to make a double bond. So we're trading an unshared pair for a bond or a shared pair of electrons. And you end up with a structure that looks like this. We do a final count to make sure all the atoms have 8 valence electrons. So 2, 4, 6, 8 around carbon, which is why we did that. 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around this oxygen. I've got 2, 4, 6, 8 around this oxygen. Okay, you may be wondering, what if I decided that I was going to grab electrons from this oxygen or this oxygen? Does it matter which one I get the electrons from? The answer is no, it does not matter. In fact, we'll talk about this later. That's called resonance, when you have more than one place you could get electrons from. Carbon and oxygen each have 8 valence electrons now, so they're all happy. The only thing we have to do now is, because this is an ion, we've got to put brackets around it and put the charge on the outside. That's what we did there. All right, the next video is going to include some example problems for you guys to work. Make sure that you at least watch some of them, because we're going to talk about expanded octets. That's something that was not covered in this video.